binary trees as our lecture today. We've talked about that one of the main purposes of this course is to go over what we talked about: algorithm analysis. What else? What's that? Recursion. And the third major component, data structures. And we've covered several data structures. Mainly we covered linked lists, we covered stacks, we covered queues, right? And now we cover binary trees. Okay, so we're going to talk about what are binary trees, what are trees in general. It's a very important lecture. So here's an outline. I'm not going to read to you the outline. Y'all can read it later. So trees, yet another abstract data type that we learn in this particular course. It's a data structure that is made of nodes and pointers. So I said we're always going to be dealing with pointers. Very similar to the concept of a linked list with respect to the fact that we have nodes that are pointing to other nodes. The difference is how they are organized. A linked list, we have a linear structure, right? We have one node pointing to the next node, which then points to the next node. We have that predecessor-successor relationship, where a tree, on the other hand, we have more of a hierarchical relationship. We have a parent-child relationship. So instead of one node just pointing in one direction to one other node, we have a node that will have perhaps multiple children and will point to all of those children, and those nodes in turn have children and point to all of those children. And somebody can be wondering, who thought of that? And again, wouldn't we like to slap them? But there's purposes which we're going to get to and benefits of using trees, specifically binary trees, that we're going to get to at the end of this lecture. So we have children nodes, and then every node will usually have parent nodes, except for one obvious one that we'll get to. So general tree information, the top node in our tree is referred to as the root. It's the root of a tree. It does not have a parent because it's the root. It's the first node, so it won't have a parent. Every node in the tree can have children nodes. Okay, so you can have multiple successors, multiple children node, and each child node can in turn have multiple children nodes. Nodes that have no children at all are referred to as leaves. So if you don't have a children, you don't have a child or children, you're referred to as a leaf node. This is just a little terminology. Any node that is not a root, does not have any children nodes, is referred to as an anterior node. So if you do not have any leaf nodes, you're considered an interior node. And the last thing we define right here on this page is the height of a tree. That the height of a tree is defined as the longest distance from the root to the longest possible or deepest possible child down that tree. And it'll be clear in a few more slides. Okay? And then I also put that a tree with only one node, so if a tree has only one node, and that's it, meaning it's the root, and it doesn't have any parents, that tree is considered to have a height of 0. So here is a picture of a tree. So here's our tree, okay? 2 is clearly the root. We have several leaf nodes, right? This is a leaf node, 5, 11, 4, those are all leaf nodes. And then we have our interior nodes. Not a whole lot to look at, just a picture of a tree, okay? But for most of us, we haven't seen a tree. We need to get used to this data structure. And again, we're going to talk about the benefits for this particular data structure. But now we go over what is a binary tree. A binary tree is a particular type of tree where we put a restriction on that tree. That every child can only have 2 nodes. Bad economy, whatever the case is. Can't afford more than 2 nodes as each parent. That's just the law. Every child can have a maximum of 2 nodes, period. So either you have no children, you have 1 child, or you have 2 children. And a child can only have 1 parent. A child can only have 1 parent. We use pointers to identify our left and our right children. So here's examples of 2 binary trees. We have a simple one parent tree, where this one parent right here, this root, has 2 children, and we have this other tree. But notice that every node has at most 2 children, and none of the nodes have multiple parents. Examples of 2 trees that are not binary trees. It's not rocket science. Who can tell us, hand the name, why this is not a binary tree?
Because so has 3.
Hand the name.
Alex.
Alex.
Only has 3.
Because it what?
It has 3.
It has 3
nodes.
3 children, and you can only have 2 children. Why is this one not a binary tree? Name? Caitlin?
Because one of the children has 2 parents.
Because this particular child has 2 parents. So those are clearly not binary trees. We would love these type of questions on tests because these aren't quite very difficult. More goodies for binary trees. The idea of a full binary tree and a complete binary tree. Full binary tree that every node other than the leaves has 2 children. Okay, so if you study this tree, we see that G, H, E, and C are leaves, but the other nodes, A, B, and D, all have 2 children. That is by definition a full binary tree. We also have what is called a complete binary tree. This is just terminology. What is a complete binary tree? As you see, but I could have left a couple nodes off here on the last level. A complete binary tree, definition, that every level, so the top level, next level, next level, next level, that every level is completely filled with the possible exception of the last level. People are really getting a kick out of this guy sneezing. I don't know why it's so funny, but we'll laugh if you want. We're laughing at you, Alex. No. Sneezing, allergies. Okay, that every level is filled with the possible exception of the last level, which if it's not filled, will be filled, and every level is filled from left to right. So this is clearly complete tree because every single node is there. But even if like these nodes 12, 13, 14 weren't there, this would still be a complete binary tree. So we talk about that the root is considered level 0. It's important to know. The root is level 0. Who can tell us, who can count is really the question. What is the height of this particular binary tree? Hand the name. Name? Stephen? 4. Close? 3. Only because we said that the height of a 1-node tree is considered 0. So we have level 0, and the countdown 1, and the height is by definition the longest or deepest path. So this would have a height of 1, height of 1, height of 2, and height of 3. So the height of this particular tree is 3. The level of any other node is simply one more level than its parent. That's pretty clear. And there's a couple of equations. I'm not even going to go through them in detail here, but you will be expected to know them and perhaps use them. We talk about the total number of nodes in a complete binary tree. Okay, the maximum number of nodes. Imagine a tree, just picture it. Imagine a tree that has 1, 2, let's just say just 3 levels, okay, including the top level 0. 3 levels. What's the maximum number of nodes that tree can have? Hand the name. Stephen? 7. 1, 2, 3, right? And the next level will have 4, so 7 nodes. So in the next, if it had 4 levels, right, it would have how many nodes? 15. 7 plus 8, 15. So look, if we have, let's say in this case, this is 4 levels. We just agreed that if we had 4 levels, which would be a height of 3, right? 4 levels would be a height of 3, that we would have a maximum of 15 nodes. And indeed, if you do that, 2 to the 3 plus 1, the height is 3. So 2 to the 4 is what? 16. 16 minus 1, 15. That's your equation for the total number of nodes. Given the number of nodes, we can also, which is n, we can also find the height of our tree. So if you have 15 nodes, you can actually calculate the height of your tree to be a height of 3. Implementation. So here we're finally now getting to our actual way we store in memory our node of our tree. So as I said, just like with a linked list, we have usually in the most basic structure, we have a data member, which we usually call, and universally in textbooks, just an int data. The second member is a variable, usually called next, that is just a pointer to the next node in memory. Similarly, for trees, it's the same type of data structure. We have a basic integer as our data member, and then we have now 2 pointers. One that points to the left subtree and one that points to the right subtree. So our struct tree node, int data, and we have 2 variables. You can call them what you want. You can call them left and right. Here they're called left child, right child. The point is we have 2 variables. Both of them are what type of a variable? Struct tree node. They're a pointer, which stores an. Y'all already forget the bonus? Pointer, which stores an address. Okay, so each one of these are pointing to an address that would ideally house in memory a struct tree node. So we're pointing to the left and right child, and here's just a visual depiction of what we should be expecting from that. So our data member and our left and right child. Traversal of binary trees. This is actually the main portion of today's lecture, and it's actually an easy portion. Really, it's going to be Wednesdays and Fridays lecture. I'm just plugging that. that are going to be, especially Friday, is a difficult lecture. This is just understanding what a binary tree is, not a big deal, and then we go over the traversals, which are really easy to do. So we need to have a way of traversing this tree. And that might be something that you might think, why would we even have to discuss that? Because when we talked about linked lists, we have to have a way of, zipping through, as I say here, the linked lists. How did we do this on linked lists? Pretty straightforward. Name? Andy? A while loop. And we simply did what? We simply took and stepped one node over, one node over, one node over. Why was that easy to do with a linked list? Because linked lists have a linear structure. There's only one way to go, okay? You go over. But on a tree, which way do you go? Do you go left? Do you go right? Do you go all the way down, then back up, then go another way? So there's a variety of ways that you can go about traversing a tree. So this is why we discuss this, the tree traversals. So you can't just traverse a binary tree in this linear fashion. There's more to it than that. Turns out there's 3 specific ways that we're going to cover for the main portion of this lecture of how you traverse binary trees. They're called preorder, in-order, and post-order, and we're going to go through each one. But before we do, I first want to describe, just in general, what is the idea of a depth-first tree traversal. So given this tree, and I have circled in green, if you can tell, the nodes N and J, because I simply want to point out on what is called a depth-first traversal, is you effectively want to traverse or go as deep as you can in whatever direction you choose, go as deep as you can down the tree before, and then back out and do that before you go in any other directions. That's the idea of the depth-first traversal, to go as deep as you can. So for example, after searching A, B, and D, you're then going to come back out to B and come down this way. So the message of this particular slide is that this node N will be searched and found or traversed before we get to J. So that's a particular idea. That's the idea of a depth-first traversal. Who follows? Not a whole lot to that. So now we have 3 types of depth-first traversals that we need to go over. So preorder, in-order, post-order, and the names are chosen according to the step at which the route is visited. So we have specific ways that we're going to show you how to traverse a tree with depth-first traversals. So preorder, the route is going to be visited before we go left and before we go right. With in-order, we visit the route between going left and right. So first we're going to go all the way left. Then after we've done that, then we're going to come back and visit the route. Then we're going to go all the way right. And finally, with post-order, the route is visited after we go to the left and the right subtrees. So we start with preorder. And I've been saying the word visited, that the route is visited either before, between, or after we go to the left and right subtrees. When I say visit, in our case, we're trying to traverse and we want to print. When I say visit, for the sake of this lecture, I mean print. So when we visit the route, we will print the route, and we want to show you how we print these traversals. Did I have a question? No? Good. So here's our code. Preorder. This is a function. What are we sending over to this particular function? We need to access the tree, right? So we're going to send over the root of our tree so we can access the tree in the same fashion that you would send over what with regards to a linked list? What do we send over if this is a linked list? Name? Caitlin? The head. So don't be confused. Just like with linked lists, you send over the head of the list. For trees, we always need to access the tree. So we need to send over the root of our tree. And it's a void function because we're not returning anything. We simply want to print out our tree in a preorder traversal. And preorder traversal said that the root is visited before the right and the left, or in this case, I don't want to say it in the proper order, the left and the right subtrees. So look at what we do. If P does not equal to null, as long as we have a tree, is what that says, and we should get that. If P does not equal to null, do what? Print the data value at P. Print the value at the root. Then do what? Then we need to go all the way left and keep performing these 3 steps. Then we're going to go all the way right and keep performing these 3 steps. So I want you to pay attention. We have 3 steps here. What are the 3 steps called? Print, left, right. Who follows? So when we initially call the function and we're at the root, we have to perform 3 instructions, and you're going to see why I'm going to break this down like this. We have to perform 3 instructions while visiting that root. We need to print the root. We then need to go to its left child. We then need to go to its right child, and in those 3, in that order. So for example, after we print the root and we go to its left child, how many instructions do we have to execute for that left child? Hand a name. Name? Rob? 3. When we go to the left child, that left child now has 3 instructions. We need to print it. We need to then go to its left. We need to then go to its right. Who follows? The examples will make it clear. So here's a small little tree. Word A. Okay, we send over the root of our tree. What do we? A has 3 instructions. What's the first instruction of A? Print it. Done. The next instruction of A said, go to the left. So we come down here to B. So now we're at B. How many instructions does B have? Rob just said 3. We have 3 instructions for B. What's B's first instruction? Print it. So we print B. What's B's second instruction? And walk through every step. B's second instruction is go left. Well, there's nothing left. And what did the code say? So let's just say we're now going to send over B's left pointer. And what does B's left pointer store? Null. So when we send over B's left pointer, sorry, I'm come back. We send over B's left pointer and we recall the function recursively. What's going to happen is, if P does not equal to null, it's not going to even enter into here, right? It's not even going to enter into those and execute those 3 lines, and there's nothing to execute. So we print A, we then print B, we go left, null, nothing to do. Then we go right, that's B's third instruction, null, nothing to do. Now B is done. We finished B's 3 instructions. So think about your function stack. What's the next instruction we were at? Hand the name. Name? Go ahead, right there, blue shirt. You looked away, he forgot. No, name? Andy? Beautiful. We haven't done A's third instruction. Who followed that? Good. We haven't done A's third instruction, which was to do what? Go right. So now when we go right, we're at C. C has 3 instructions. What do we do with C? Its first instruction, print it, done. Then we go left on C, and then we go right on C. So that's that example. A very small example, easy to do, and even this one, on this next example, is easy to do, but mistakes can happen, and you're going to see why, because each one has a slightly different order. As a result, I always encourage students, and I'm really happy when I see even the best of students do this on the exam. Don't try to think, oh, I'm too good for it or whatnot. I really encourage students to put down next to every node the 3 instructions. In this case, what are the 3 instructions? PLR, in that order. So if this is an exam, I encourage you, write down next to A, really small, put PLR, 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 PLR. Write down PLR next to every node, and as you perform that instruction, you scratch it off. So you know what you've done. Seems cheesy, but it happens all the time. People will be like right here, and they're like, snap, what do I do now? I printed I. I mean, you get so many function calls in your head, you forget where you're at. So I really encourage that. It helps a lot. And I like it, as I said, when even I see the best of students who do that, because again, why make silly mistakes? Because it's too easy to make a mistake on. So we explain this one. A, we send over the function, the access to our tree. So A has 3 instructions. What's the first one? Print A. Done. Then we go left, come to B. B has 3 instructions. Print B. Then we go left, come to D. Print D. That's its first instruction. Come to G. D's first instruction is to print D, is to print G. G's second instruction is go left. G's third instruction is go right. G's now done. We come back to D, and what instruction are we at? D's third instruction. Good. So now we come to H, because D's third instruction was go right. We print H. H is the second instruction, go left. Third instruction, go right. H is done. D has now completed its 3 instruction. Where are we at? We're at B, and we're at B's third instruction. Who follows? It's not hard to follow as long as you come to class and you're awake. We're at B's third instruction, which says go right. We're at E. E has 3 instructions. Its first one is print. Then we go left. There's nothing to the left. Then E says go right. Okay, so every node has these 3 instructions. When we go right, we come to I. We print I. Then we go left and right. Done. We back out. I's done. E is done. B is done. We come to A. A's third and final instruction is to go right. We go right to C. We print C. C's second instruction, go left to F. We then print F. That's its first instruction. F's second instruction is to go left. There's nothing to the left. It's null. So then we perform F's third instruction, which is to go right. We come to J. J has 3 instructions. We print J. J has 2 more instructions, which is to go left and then go right. After we've called J's right, and we've done that instruction, we've printed everything, but a good question would then be, a good quiz test question, what would be the next instruction that is immediately going to be performed after this? Hand the name? Guy? C right. Who follows that? Good. That means y'all are following. So, because after we back out, we're done with J, we're done with F, and now we come to C, and that's the last instruction to perform. We have to go to C's right, which is null, and now we're done. So this is preorder, straightforward. They're all the same, they're all similar, it's just the order in which you process. In order, the root is visited between the left and the right subtrees. Okay? The root is visited between them. Again, when we say visit, we mean print. And here's our code. So again, we send over access to the tree. As long as we have a tree, we need to perform 3 instructions. Or as long as that particular node is there. Because now it's not just about the tree, right? We understand it's recursion, that we go through the nodes. As long as a node's there, we perform 3 instructions. So first of all, hands high. I'll take a moment to reflect. Look at this code. Hands high if we understand the code. Keep your, now put your hands down. Now see. I'm not trying to be funny, but this code is now, it's a function. It's using recursion. We're recursively calling this in-order function twice, and we say we understand it. So hands high if you now realize, not trying to be funny, but serious, if we realize we're getting a little bit nerdy. I say that jokingly. Some people get upset. He's calling us nerds. No, realize, I want you to be proud of where you've come, right? Because understand at the beginning of the semester, we don't even know what a pointer is. What's a pointer? Like I asked, like nobody knew what a pointer is. Couldn't even answer the question. And now realize that we're looking, I got this. Like, look at this code. It's using recursion. No problem. We're good with that. So feel good about that, where you've come. So we have 3 instructions. We call the in-order function. We recursively to the left, we then print as the second instruction, then we go to the right and we call it again recursively to the right. So let's look at our example. A has 3 instructions. Again, I encourage you, write them down. What are the 3 instructions? Can somebody tell us with just the letters? Name? LP, and he's getting confused. R, yes, it's picking on you. LPR. Write LPR next to every node. So A, its first instruction, go left. B's first instruction, go left. Then B's second instruction, print. B's third instruction, go right. So the first node printed will be B. So now B is done. We go to A. A's second instruction is print. Done. A's third instruction, go right. C's first instruction, go left. C's second instruction, print. C's third instruction, go right. Who follows? Hands high. It's easy. It's cake. Okay? Here's a bigger one. Not any harder, just bigger. But again, it's like the 4th time saying this, right? You want to write down those 3 instructions because mistakes can happen. So, what are the 3? L, P, R. You see, you think I'm trying to say it to remind you. I'm really trying to remind myself as I go through it. L, P, R, next to each one. So at A, we go left. We come to B. B's first instruction, go left. D's first instruction, go left. Now we're at G. G's first instruction, go left. G's second instruction, print. Done. G's third instruction, go right. Now, G is finished. We come back to D. What's D's second instruction? Print. Done. G's third instruction, go right. H's first instruction, go left. Second instruction, print. Third instruction, go right. Now we come to B. B's second instruction, print. Done. I'm not getting any oohs and ahs on the animation. That's horrible, especially for the video. I need some oohs, right? No, actually don't, because then we'd be oohing and ahhing the whole time. So anyway, B, we now go right for B's third instruction. We come to E. E's first instruction, go left. Print E. E's third instruction, go right. Now we're at I. I's first instruction, go left. Print I is the second instruction. And then we go right for the third instruction. And guess what? I is now done. E is now finished. We finished B's 3 instructions. Now, how would you know that you finished B's 3 instructions? Well, either because you were really good at it and you practiced it a lot, or you wrote down L, P, R, and when you first went left, you crossed out the L. Then when you finished this and you printed the B, you crossed out the P, and then after you printed the B and you went right, you crossed out the R, so you know you're done with B. So after you come down here and you print I, you're like, oh, where am I at? You didn't sleep last night before the exam and you're struggling. You know where you're at because you know you're done with I, because you've crossed out those 3 instructions. You know you're done with E. You know you're done with B. And now you're back to A. And A's at its which instruction? Second instruction, which is to do what? Print. Print A, then we go left. We come to C. C's first instruction is to go left. F's first instruction is to go left. F's second instruction is to print. Done. Third instruction, go right. J, first instruction, left, then print, then right. And we're done? No. Not done. And the way you would know you're not done is if you wrote your stuff down, if you paid attention. So J's finished, F is finished, but we never printed C yet. We only did one of C's instructions, which was to go left. So now we need to go right, and then, now we need to print the second instruction of C, and then we go right, and we're done. Who follows? Good. In order traversal. Post order is simply where we print after visiting both nodes. Let's run through this one. Visiting again means printing. Here's our code. I think we get our code by this point. We print after we recursively go all the way to the left, and after we recursively go all the way to the right. So in this case, A's first instruction. What are the 3 instructions of A with letters, hand, and name? Somebody new? Yes? Sorry. Sean? LRP. I got to think about that. I'm tired. I slept like 3 hours. LRP is correct. So we need to go left, then right, then print. So A's first instruction, left. B's first instruction, go left. B's second instruction, go right. B's third instruction, print. So B is printed first. Now we come back to A. Print A? No, because we're at A's second instruction, which is to do what? Go right, and we come to C. C's first instruction is to go left. Second instruction to go right. We print C, and now I will tell you, I'll just plug it for those who are here and awake, this is the common mistake, and that is after we've done the 3 here, because in this case, when we are doing a post-order traversal, what's the very last thing to print? The root. The very last thing that gets printed is the root, because after we've done C's 3 instructions, there's one final instruction, and that was A's third instruction, which was to print itself. So the final thing that happens is printing the root, and when you get a big example like this one, people will print out the whole thing. So I'm telling you the mistake now, so hopefully you pay attention. People will print the whole thing perfectly, except A. Because at the very end, and they're so proud of themselves, I did it! And then they forgot to print A. So just because they forget the root at the very end, okay? So anyway, that's why I plug it and warn you about it. So here we go. Doing post order. So L, R, P, left, right, print. So A, go left, B, left, D, left, G, left, and go faster. Left, right, print G. Done. D, second instruction of D, we need to go right. H's first instruction, left, then right. H's third, print. D's third instruction, print. B, it's at its second instruction, go right. E's first instruction, left. E's second instruction, go right. We're at I. I has 3 instructions, left, right, print. Now we print E, we print B, so you see it print each individual root as you back out. We come to A, A's second instruction, go right. C's first instruction, go left. F's first instruction, go left. F's second instruction, go right. J's first instruction, left. J's second, right. J's third, print. F's third instruction, print. C's second instruction, go right. So I like these type of little questions. After F prints, what is the exact next instruction? It's to go right at C. Then we print C. Then the last step, don't forget, print your root. So those are our traversals. And we're not going to do this as just for you. This is to practice, but there's really big examples at the end of this set of slides. But these are just 3 to practice with: pre-order, in-order, post-order, and there's your solution. Can y'all see that? And this was taken 2 semesters ago. I need some pictures from y'all. I'm going to try to make them daily bike fails, UCF bike fails. Hate that we're making fun of ourselves here, but it's not us, right? As we said. This was in front of the union. The reason why you know is a couple semesters ago, because I guess they finally realized, again, I'm not trying to be mean, but we call it the human stupidity pictures, that where there's a lack of intelligence from some of the UCF community, and that everybody's always, this is a double bike fail if you can tell, right? So we have 2 bikes, 1 on each side, safely locked up to this post. So, but if you've noticed in front of the union, they've removed these things, right? Who's noticed that? So they're there. I can only guess this is part of the reason why. You know, we get things about, you know, bike theft all over campus. It's not bike theft. It's just teaching stupid people a lesson. No, I'm just sorry. No, but here we are. No. So bottom line, they removed these things, and I got a great picture of, you know, coming up later in the semester where we still somehow fail because they replaced those posts with the little, whatever you call them, I don't know what they're called, swirly things. And people still manage to fail, but we'll get to that later. So anyways, that was just a funny double bike fail that was taken a couple semesters ago. So actually, and so I'm referencing, you get to plug yourself, right, for the whole class. That was from Joe, but Joe was 2 semesters ago. Yes?
I have a question for the program.
Question for what?
For the program.
For what?
For the program.
Are you serious? In the middle of the lecture?
No, I thought you were not.
He's really motivated. That will have to hold off. No, this is our midpoint, right? Alex, you gotta work with us. What's your last name? You're gonna be on YouTube also. So here we go. We're gonna talk about breadth-first traversals now. We talked about depth-first traversal, which is to go as deep as you can before you back out and then go in another direction. And you saw by the 3 examples of pre-order, in-order, post-order how we do that. But each one goes as deep as you can before trying to go in another route. The breadth-first traversal, the idea is that you want to traverse one level at a time. You want to go as wide as you can before you go deep down the tree. That's really all you need to know in general behind what is a breadth-first traversal. So I'm not even going to read all this to you. The bottom line is, instead of N being visited before J, in this case, J is certainly going to be visited before N. This is the idea of a breadth-first traversal. In code, you would simply need to know how you plan on traversing this. You want to go left to right, right to left, and choose how you want to implement it. But you basically, one level at a time is how you traverse and you zip through this particular tree. So, I mean, would I have to even like explain? If I just simply say left to right, does this need, who could already answer this? I'm not going to call on you, but hands high if you could already answer this. It's not a lot, hold on. Not that you're like, I'm being punked or something, but hands high if you can answer this. That's a little better, okay. Because all you do, one level at a time, left to right. So literally, we should all be able to say HDL, BFJN, ACE, you know, all the way to O. And it's a shame when this question is asked. It's not many miss it, but it's about a 5% miss rate on the exam every time. Just people weren't paying attention, that's all. But anyway, so that's not hard to do. What I want you to spend a couple of minutes on is how would we implement this? And for those who've read the slides or are looking at the slides, don't ruin it for the rest of us, because the reality is you would never think about the answer. I'm sorry. Unless you're like just a genius guru, most people wouldn't think about the answer of how you would implement this. Okay, so who already read the slides or you know how to implement it somehow? It's okay, raise your hand. Okay, so don't answer. But I want you to think about, we just showed you how to implement with the depth-first traversal for pre-order. What do? We printed it. We then recursively went all the way left. Then we recursively went all the way right. That was pre-order on a depth first. So think about what we did with the depth first traversals, the pre-order, in-order, post-order, how the 3 lines of code, they were print, then go left, right, or go left and print, go right. How would you implement this in code? I want to spend a minute and just think about it, then I'm going to show you the solution. It's a very cool solution. How would you implement that? Any idea? Just think out loud. Worst scenario, we laugh. Yes, name? Steven.
Print left, print right, print.
Somebody might come up with a great solution. So say that again.
So you print the first node, go left and print that node, and then right and then print that node.
Okay, so how do you do that though? In code. You're right. I mean, yeah. So you're saying we need to print H, then we need to print D, then we need to print L, and then we need to print B and F. So you're saying what we need to print. But how do we make that happen with code? Yes?
You do recursion, you do first print, and then you go left, and then right, and then you do recursion again, call it to have print the print, and then go left, and then right, and then recursive again.
Are you asking about the program right now?
No.
Okay, I'm just joking with you, Alex. I'm just busting your chops. No. Honestly, I didn't follow that, but you'll understand the reason I didn't follow that, because there's one solution to this. And it's a beautiful, elegant solution. But you were saying print, then go left, then go right.
Recurse.
So then recurse left, then recurse right, then do what?
After you prints and then goes left and then right, and then calls again itself again, then prints left print goes left.
The problem with that is when you see the first instruction is print, then left, then right, then you have other instructions, right? So forget those other instructions. What's going to happen is after you print H, and then you go, H's second instruction is go left, what's D's first instruction? It's going to print, but then what's D's second instruction? Go left, and then it's going to print. So let me just show you the solution, because the solution is beautiful and it's elegant, and it uses another data structure that we've already learned, namely queues. You want to traverse and print out the nodes? Do the following. Then I'm going to go back to the picture, and you're going to see how beautiful it is. Enqueue the root. That's step one. Once you've enqueued the root, so now the root is in a queue, right? And the queue is what? First in, first out. So you enqueue the root. Then you simply perform the following instructions within a loop. While there are nodes in the queue, and are there nodes in the queue right now? Sure, we just enqueued the root. There's one node in there. While there are nodes in the queue, the three instructions are print that node, enqueue its left and right children. It's a second instruction. Enqueue its left and right children in that order. Enqueue the left, then the right. Then dequeue that node that you just printed. Okay? So dequeue, well, I went in reverse order, it doesn't matter. Dequeue the node. So we have one node in there right now, the root. Dequeue it. Then you're going to print it, and you're going to enqueue its children, or maybe I said it reverse. So print it, the node you just dequeued, print it, then enqueue its children. Who follows without more explanation? I'm going to explain more. I'm just curious who follows. Hands high? Okay, good. So, but we'll explain more. So continue this process until there are, as the while loop states, no more nodes in the queue. So if we just back up and we look at this pretty picture, we first enqueue the root. So H is in the queue. We haven't printed anything. This is what we ultimately want to print. H is in the queue. What does the instruction say? It says dequeue, print that node that you just dequeued, and then enqueue its children was the third instruction. So dequeue H, H is in the queue. Dequeue H, so now the queue is empty. And what do we do after we dequeue H? We need to print H, done. Then we enqueue its children. So now D and L enter the queue. So we're in a while loop. What does a while loop say? State, continue doing this until there's no more nodes. Are there nodes in the queue? There's two nodes in the queue, D and L. Well, what do? Dequeue D, then print D, then enqueue its children, B and F. So now what's the next node in the queue? Hand the name? Jordan? L's in the queue now at the front. Dequeue L, print L, then enqueue its children, J and N. The next node in the queue, hand the name? What's the next node at the front of the queue? All the way in the back? Rob? B. B is at the front of the queue. Dequeue B, print B, enqueue its children. Then the next node at the front of the queue is F. Dequeue F, print F, enqueue its children. Who follows? So we're using one data structure to print the traversal of another data structure. Very elegant with the use of queues. Kind of cool, kind of nerdy, whatever. So that was our solution for queues. What's next? Binary search trees. And this is the last part of the lecture. So we've seen how to traverse binary trees. Okay? So it's great. People can be like, okay, I know how to go this left-right stuff. You have nightmares of going left and right. So I know to go left, right, and print. I know to do the three traversals. But a very important question we should ask is what? Okay? What the heck is the purpose of binary trees? I haven't even discussed that yet. I mean, I'm glad y'all are awake and following me. But I haven't even talked to you about the benefit of trees till this point. I just explained, hey, we have a tree data structure. You know, tomorrow we're going to talk about forests, and then on Friday we're going to go over jungles, you know, like the weird data structures. I mean, y'all are just following along like, okay, these are trees, I know how to traverse them. But what's the purpose? It's rhetorical. What's the purpose of a binary? He wants to ask about the program again. What's the purpose? What's the purpose of a binary tree? The purpose is when, there's many purposes, but the main purpose is when we then put a restriction, another restriction. So for the first restriction, we took a tree and we made it into a binary tree, which was what? Quickly hand the name. Clay? 2 children max per node, binary tree. So now we want to put another restriction, which I'm not going to point out to you. I want to see if you can figure it out. Look at this tree. Spend no more than 20 seconds. Look at that tree and try to identify what is special. We put a restriction on the data values within each node. What is special about this tree? 10 more seconds. I'm not going to call anybody. I just want to ask, hands, who thinks they see what's the pattern or what's special about it? This is a binary search tree. And I say, what pattern can you see? What we see is, for any given node in the tree, all the nodes to the left of it, to your left, all the nodes to the left of it are smaller than that node. So look at 6. All the nodes to the left of 6, there's only one, is smaller. Look at 8. All the nodes to the left of 8 are smaller. And for any given node, all the nodes to the right of that node are bigger. So again, look at 8. All the nodes to the right of 8 are bigger. All the nodes to the right of 10 are bigger. But even it holds here at 14, all the nodes to the left of 14 are smaller. This is the rule and the restriction, one second, for a binary search tree. And I say, why might this property be desirable? Because it's going to make searching super fast. If this was, how many nodes do we have? We got 5, we have 9 nodes. So if this was a linked list of 9 nodes, worst case scenario, how many nodes do we need to traverse in order to find a node we're looking for? Hand the name. Quickly, it's an easy question. Linked list, 9 nodes, worst scenario, how many nodes do we need to traverse through to find it? Name? Nick? 9, right? In this case, the worst case scenario is going to be log of n. We're going to explain why. I think many of us perhaps already follow that. But if we're looking for 4, how would we find 4? We're going to say 4. So we start with the root. Is 4 going to be left or right of 8? Well, first you'd say, is 4 the root? Is 4 the node we're looking at? No. Is it left or right of 8? It's going to be left of 8. Who follows that? I want to make sure there's something simple you follow. 4 is clearly to the left of 8. Then we say, okay, we come to 3. Is 4 to the left or the right of 3? It's to the right, because it's bigger than 3. It has to be bigger than 3 if it's in the tree. We come to node 6. Is 4 going to be left or right of 6? It's going to be left. So indeed, when we come to the left of 6, we come to 4, and we found our node. So we only had to do 4 comparisons, and we ultimately found our node as opposed to doing 9 comparisons. So searching gets very fast. Instead of being O of n time and a linked list, now we have log n time, which I'm going to explain more in detail, because of this ordering property, which tells us look to the left or look to the right based on your values. So this is what I just stated. I'm not going to read that again. So look to the left of the right subtree. This is the just in more detail, just re-explained. I explain it twice for going left and twice for right. But I think we get the rule is for every node in the tree, the rule stands for that node that all nodes to its left have to be smaller, and all nodes to the right have to be bigger. We've got 2 minutes. So this is an idea of a binary search tree. You could examine it and confirm that all nodes do indeed follow that particular property. Why is this useful? It's useful for fast, efficient searching, because what we have effectively done, this is what's cool, what we've done is we've taken what we learned in the first week of the semester. We learned about binary searching and how binary searching is log in runtime. So instead of searching through a billion nodes, you search through 30 nodes. We've talked about many times. So here we've effectively embedded a binary search into a data structure. That's cool. We've taken a binary search and the strength and the efficiency of the binary search, and we've embedded it into this data structure, our tree. Finally, I briefly mention that the insertions of nodes, therefore, have specific rules when we insert. We can't just insert arbitrarily. Insertion has rules. Deletion has rules. Those will be Wednesdays and Fridays lecture. Historic, maybe actually, that might be a good word. Maybe historic. And finally, our demotivator. I love it. Doubt. In the battle between you and the world, bet on the world.